Great pleasure to welcome Duc-Lam Duong as our next speaker.
Right, so thank you very much for the introduction and for having me here. It's a great pleasure to be here. So I've been here a couple of times, so it's really nice to be back. I will talk about some work that we have done recently on using diffusion model in sampling of nonparametric inverse problems. And so this is a joint work with Fabian Schneider, Tabo Helin, who is here, with Matti Latsat from Helsinki University, and Martin de Hoop from Rice University. So Fabian is the main architect behind this project. He's done most of the work here. So this work is supported by Research Council of Finland through the Center of Excellence and the FAME flagship funding. So let's formulate our framework. So a lot of problems in science and engineering can be formulated as an inverse problems of finding the unknown through some indirect and noisy measurements. Here we denote unknown by x, and then measurements through ax plus some Gaussian noise. So what is challenging about inverse problems in general is that they are usually ill-posed, which due to the fact that we have noise, we have sometimes the unknown can lie in very high or infinite dimensional space, where you only have access to finite data. And also sometimes the forward map can be very challenging to obtain the full knowledge. And also another challenge on top of that is that for many inverse problems, the computation of A can be very costly, or even sometimes impossible. We always have to do approximation, and so on. Right, so the Bayesian approach to inverse problem is now a standard in this field. So we will consider that the unknown lies in a Hilbert space, and then the Bayes theorem will give rise to some posterior measure, also living in the Hilbert space, given some appropriate prior mu. The problem is that although this setup will give you usually a well-posed posterior, in the sense that the posterior will it will behave continuously with respect to the changes in the model and the prior as well. However, to be able to extract information from the posterior usually require a very large computational effort. And especially in the case where the forward map is very expensive to compute. So what we do is that we will try to leverage the diffusion model here. So just a very quick recap. We have seen diffusion models throughout the week. So basically, score-based diffusion models are generative modeling techniques that try to learn sample from some complex distributions by gradually denoising a normal distributive random variable. So this picture is taken from paper of Zhang Shou. So usually we have two processes involved in this diffusion model. That the forward process usually easy, and then the backward or time reversal process, which usually causing troubles. And on top of that, because we are forming our problem in infinite dimension, So we run into problem of defining this score function. This score function in a way that it is well defined when we don't have any densities here. Because in finite dimensions, you can always define density with respect to the Lebesgue measure or Lebesgue measures. And so this has been recently dealt with by a series of works, including work by Pichtigart, Joseph, Sebastian, and Sven. I think Sven is around here. Maybe you can ask him related to this. So that is, I mean, it's nice that this framework can be extended to infinite dimension, but then there are so many other challenges arises in this framework. Just to quickly recap in infinite dimension, so the forward or noising process is quite simple. We start with some SD, let's say some Ornstein-Uhlenbeck process, associated with some with some, now C is some covariance operator, so this noising process is quite simple. Everything works like in finite dimension, so nothing to be worried about. For the backward process, you need to define the drift here. Here we denote it by S, and this S is a score function which can be defined by this formula following the work by Pichtigart and others. And the important thing is that this look like strange-looking formula actually the same when we consider the function the space to be finite dimension. Then we recover the usual score function, of course, with a little bit of some weighted of the covariance there. Right. So naively, we would like to replace this prior with some posterior, and then try to learn some the conditional score from some training data, and this can be done. For example, you can just explore this structure of the conditional score. So here everything is still in finite dimension. So in this talk, anything in finite dimension, I will use Q or P just to denote that we have densities. In infinite dimension, we have the measure mu. Right. So you can draw this to be just by Bayes theorems, you can draw it to be the unconditional score plus the likelihood term. So this is like a measurement matching term. So a lot of work has been done in this direction that can be grouped into mainly three directions. So this is very unbiased. Very biased literature. Of course, there are so many others, resemble these, but we group here the three main directions in this frameworks of using diffusion model in inverse problems. So the first one use some correction terms to add to the unconditional score, and through different ways. For example, they can use the work by Zalard and al. They use a score-based SD with some data consistency, or projection-based approach, and so many others like follow similar approach. However, these approaches in this direction, they fall into this limitation that you need to require to evaluate the forward map multiple times during sampling. usually for each samples, you need to evaluate this forward map a lot already. And then the second group use Langevin type MCMT algorithms. This also proved to be quite successful. However, again, it looked quite challenging in high dimensions, and this scalability is not always obtained. The third group will try to learn some amortized conditional score, and one of the leading work in this is like in Basolis and Barasaris and others. So instead of trying to approximate this conditional score, they try to learn this conditional score itself or some amortized version of it. But again, this is quite challenging because it requires some extensive Zoid distribution training data. So we can somehow regroup this into, so the first one is approximate. So everything is approximative and you need some approximation. The second one is usually asymptotically exact in the sense that if you run the algorithm MCMC long enough, maybe you can hope to obtain the exact posterior. While the third is an exact one. So now we want to overcome. We want to leverage this diffusion model and try to overcome some of these limitation here. Now, just in finite dimension, we just look at this posterior or the diffuse posterior again and see what can we do here. So because we are considering the Gaussian noise and the forward map here, A is linear. So you can just, so this is like a Gaussian distribution, and same with here. You can do some, simple algebra here by completing the square, and then you obtain some new distribution, Gaussian-like distribution here, with some different mean and variance. All these terms can be easily computed like in closed form. So what is interesting here is that this conditional diffusion can be interpreted as a task-dependent unconditional diffusion, which pass through some alpha transformation. Now we want to formulate this rigorously in infinite dimension. So we assume that, so this is like one of the main theorem in our work. First, we assume that if we have this, the prior is supported in the Cameron-Martin space of the covariance operator C, and we denote some operator here, and then this term MT here. Now we define a random process ET tilde mu, such that its distribution is given by this mixture model. And then we denote this as ZT mu to be the unconditional score function of this process. Then we can write the conditional score function to be, this conditional score function can be rewritten in terms of the unconditional score function that we defined above, with some extra terms. So what does it give you? So well, okay. So before that, let's go through some ideas of the proof. So I will be quick on this, but so we just use this. So we write this score function in infinite dimension in this expectation form, and then we use some ideas in prestigious papers and write the expectation in some nice form, and then we use Cameron-Martin theorem together with some tricky calculations. So this is very hand-wavy, but if you are curious about this proof, you can look up on the paper. Also we did something similar to Claudia in the today talk, but we try to quantify the error or the distance between the estimated distributions and the true distribution. So we have this norm in S, average on in some distributions. This error term can be bounded away from all the error that that you run into in this this process. So, for example, this truncation term is this arises when you have to stop early, just before 0. The initial condition term is related to this t when you don't run into infinity, but you have to stop the forward process at some point at some big t. This epsilon loss is associated to the training loss, and this epsilon num is the numerical errors that related to this discretization. That, for example, this you use any approximation that you encounter into this, and all of these errors can be bounded quite nicely like this. So in some sense, it resembles a result of Claudia. Of course, I think that objectives might be quite different, but we have some similar results. Now, so that is the theoretical results, and then what can we gain from this approach? So the high-level idea. So we propose this method we call so. This could be changed, so we will update a new version of the paper on arXiv, and the name will be slightly changed, but the idea remains the same. So the high-level idea is that we simulate a task-dependent unconditional diffusion, xt tilde, given in this form, and then we train the unconditional score as tilde with your favorite method. And then you recover the conditional score using the results that I just mentioned previously. And all of this can be done in a way that the forward operator, this coming from the inverse problem, the forward operator that can be troublesome when computing, this can be observed or absorbed into the task-dependent diffusion. So in a sense, it absorbed into the training process. Right. And now, so in practice, how this works. So we just use this identity that we have previously. And now we, so on the right-hand side, this R term here is defined like this. Where S tilde is the score corresponding to the unconditional score, and S is the conditional score, and so RT here is defined like this, and this term this RT is actually some bisections on the Hilbert space H, so you can so that's why all of these are very well defined. So even here you have some inversions matrix here, but all of these can be written in a way that you don't have to inverse any matrices or operator in practice. And in training, the score matching course certify this identity, where here Z is distributed according to this. Now I will give a couple of examples how this method works. The first example is the city example, where you try to recover this inner structure of the body, or more like the slice of the inner organs of the body. Here is the posterior samples from this CT imaging problems with some fluid neural operator architecture. On the left here, this is the ground truth. This is the sinogram measurement data. And on this, on the right-hand side, you have 5 posterior samples. On this column, this is the bias, and this is the standard deviation. The method that we compare from the top to bottom, so here is SD, a new Langevin dynamics. The second one is DPS method by Chung-Eun. And the third one is a projection method. On the fourth one, we have this conditional method that I mentioned previously, where they try to evaluate exactly this conditional score. And on the last one, we have our method. So here's the statistics of the comparisons. So you can see that so our method perform usually the best in terms of time. So we don't because we don't run into evaluating the forward map anymore during sampling. So everything is shifted to the training, which is quite similar to the conditional method. However, in terms of bias and standard deviation, we usually obtain better results than the previous one. We also compare how our method perform with respect to these FNO architectures. But yeah, for the internet of time, I don't show it here, but you can look it up on our paper. Another example is the deep learning example. Again, we have the route truth here, this measurement data, and the 5 posterior samples. With here is the bias and the standard deviation. The method from top to bottom is the same as the previous example. And also we also have the statistics comparisons and other comparisons that which we have, but also you can look it up on the paper. So there's another thing I want to mention here is that all these examples are that's the first examples that we tried using our method. However, it doesn't mean that this only applies to these type of problems. So as I mentioned, maybe the most advantages of our method is that this can be applied to any inverse problems that linear inverse problems that the evaluation of the forward map is very costly. So if you have a problem like that, you can try to apply this method. So because we form it in a way that we can shift all the the computational cost of this forward map evaluation into training, so that you can do sampling quite quickly with this method. Okay, so what next with this method? Although this setup it seemed to be promising in dealing with inverse problems with very complicated forward map. However, it also has certain limitations, because we relies on this the linearity of the forward map, where you can conjugate the likelihood with the prior, so in a way that you can form another Gaussian process. So at the moment, we don't know how to overcome this limitation. However, maybe with some certain techniques like linearization, we hope that certain problems can also be applied using this method, but that remains to be seen. Also, we don't know if, for example, certain type of noise, not Gaussians, but other type of noise like boson noise or others that are used more in other examples, like in imaging or other type of inverse problems, which also run into this limitation. So we don't know how to deal with that for now. But it's also opened up many interesting questions that remain future works. Here is a paper with a warning that a new version is coming soon in a few days. Maybe the title will be changed a bit and the name of the method, but the ideas will remain the same. Thank you very much for that attention.
Do you have time for questions?
This is probably a very naive question. You mentioned earlier that methods aren't applicable because there is no density. Can you do density with respect to some Gaussian measure?
That is exactly what we do. I mean, of course, so we define in a way, not we define in a way, but other people define this in a way that you can write in some sort of like expectations. And this expectation can be written as a Radon-Nikodym derivative for Cameron-Martin theorem of some, yeah. So it goes through that route. But, yeah, but yes.
Questions? I have a follow-up question to Masha's question. So your construct bases on abstract linear spaces. And I can more or less see how you construct these based on a Gaussian measure in the first place. But the advantage of your method, if I understand well, is that you can combine this construction with non-Gaussian priors. Right? You have a Gaussian likelihood, you have a linear operator, but in the score matching phase, you relax the Gaussian assumption.
Yeah, no assumption on the prior.
On the prior. So, but you use the Cameron-Martin theorem in your construction. So, what would be the abstract Wiener space, or the counterpart of the abstract Wiener space, with a non-Gaussian prior?
That's a very good question. I think in the paper by Joseph and Sven and others, they deal with this, is it? So we somehow use this score function that defined in infinite dimension. This is coming out direct from their paper. I think they deal with this quite intensively. How you define this in infinite dimension, how you define the Wiener process that makes sense, or how you choose the process that makes sense, because there's no canonical way to do that. But I mean, the short answer that I'm not quite sure.
food for thoughts and discussions. Thanks. One last question? If not, let's thank the speaker again.